Yeah, hi everyone. So it has been a while since I made a video. I have been really busy on multiple fronts, writing articles, finishing up my build a reasoning model from scratch book. I just submitted the last chapter last week and have been working on the final edits. So I wanted to make a new video on LLM architectures because that's a topic I'm really interested in, and it's always exciting to see the new architectures coming out, looking at the research reports, the technical reports, looking at the code, sometimes also re-implementing them from scratch for, getting additional insights. And so, I have been making a video on LLM architectures not too long ago, maybe a few months ago. And there have been so many new ones, and I wanted to make a new video, but I thought I have an even better idea, something that maybe ages a bit better than a video, namely making a tool that I can use to visualize or, like, let's say, compare architectures, and that people out there can just browse. So I'm planning to extend the tool with additional architectures. But in a nutshell, what I did is I put together like an LLM architecture gallery here where all the different architectures are visualized. And it's just free on my website, like a page where you can scroll through all of them. So it's been quite some work, but I've been pulling all the architectures from all my articles together and put it on this website here. So I just wanted to show you what that is, this architecture gallery in this video. And I wanted to also maybe just talk about some of the new architecture, some of the interesting aspects, what we have been seeing, and so forth. So basically just explaining what the architecture gallery is, and then also diving into some of the details to, let's say, look at interesting technical details. And so this is mainly just an overview where there are lots of architectures. If I scroll through this, I think right now there are about 50 architectures from my various articles or social media posts that I made in the last, I would say, 1 to 2 years. And so so you find a lot of architectures here. And they are mainly from my articles that I went back to and I pulled them from, but there are also new architectures that are not in the articles yet. So just to give you an overview again, so right now it's like a very compact view to make it, let's say, less cluttered. But you can also select the more detailed view here, which expands the information here for each model. But if I also go to the compact one, because I think that's easier for scrolling, you can also go just to show details here and then show all the different details, like what type of attention mechanism do they use, what's the context length, what's the license, and and also here I have additional links. So if you want to check out the config file on the Hugging Face hub, it's just like a link where you can double check the information, make sure that I pulled it here correctly. Of course, maybe the most interesting thing is the figure itself. So you can see the figure, which I hand draw. So there's no tool for that. That's not automated. That's what I'm doing myself manually. But it's basically how I make them is I look at the config file, and often I also, of course, read the technical report that I also link. If there is no technical report available, I always also check out the code. So often there is an implementation in either VLLM, SGLang, or Hugging Face. So I check out the code. There's also a license if it's available. Some of them don't have a license available. So the license is actually quite useful if you want to use that in real life, in your, let's say, company context and so forth, or research context. So you know what the license says you are allowed to do. And also, of course, you can compare. So for example, I can take this architecture model A, or let's maybe do DeepSeek version 3 versus, what do we have here? Maybe let's go to Llama here. So we can do model B, and then it should show us like the two models here side by side. So we have a view, model A, model B, and then we can see what's the same. So they're both a mixture of experts. They have different sizes though. DeepSeek version 3 uses a multi-head latent attention. Number 4 uses grouped query attention. An estimate of how big the KB cache size is. I will get back to that in a moment, but yeah, so basically you can see like a comparison here of the different available information, what's different and what's the same. Maybe if I pick a model here that is more similar, it's maybe more interesting even. So there's DeepSeek version 3 and version 3.2. And so you can see a lot of the aspects here are the same. So they share a lot of details, except that this one now has DeepSeek Sparse attention in addition to multi-head latent attention. And also it performs a bit better on benchmarks. So here, this is the, should maybe add this. This is from the Artificial Intelligence Index. So it says that actually if you go to the individual slides here, and you can see more information here, there's an info box. So if you click on that, it should give you information how I collected this data. And yeah, and so going back to that, so there is basically the total score that is reported on the Artificial Intelligence Index. And so the Artificial Intelligence Index is actually quite a nice website. I'm not affiliated with that, but I like that because you have like an independent provider that gives you scores and everything. Yeah, where I wanted to go with that is, so you have the total score, and then you have also scores for individual categories. So for example, a general score, general knowledge, scientific reasoning, coding, and performance and agents, and so forth. So yeah, so that is basically a nice tool too if you want to compare those. But let me clear this. Just going through this again. And so if we, let's say, we're interested in what has changed over the last few months or years, I wanted to just maybe also walk you through some interesting aspects here. So you can also sort it from size alphabetically, newest first. But if I stick here with oldest first, starting with GPT2 XL. So that's like the standard LLM architecture that most other architectures are derived from. And GPT2 is the same as GPT-1 and GPT-3. So that's like the prototypical original LLM with the masked multi-head attention, no rope embeddings. It was traditional token embedding layers with positional embeddings added to them. And yeah, so that's like the traditional GPT. And then I also have, for most of them, a view an article here where you can jump to a section where I covered this model in an article. But I also have these informations here, like if view an article is like a jump to the article. If I go here, it should bring me to an article where I've written about this a bit in more detail, where you can read about it, where it has some interesting additional information. But this is usually just like more context if you need it. So most of them have in view an article if I've written about them somewhere. This compares Llama 3 to Olmo. I don't have a specific Llama 3 article, but I usually linked some article that is related. In this case, I also have a from scratch implementation, so you can go here and check out my my notebooks where I go from GPT to Llama 2, and I also have standalone notebooks for Llama 3 and so forth. So in a nutshell, this is essentially like almost like an encyclopedia of all the information I put together over the last few years. With that, there's also like at the bottom a box MHA here, like related concepts. So I made standalone explanations, tutorials based on my articles, just reformatting this a bit to make it a little bit more compact. So if you are interested in, let's say, this architecture, you see, oh, it's masked multi-head attention, MHA. What does it mean? You can click on related concepts, and then it brings you to that page, and then you see like a summary of my article where I pulled in together some of the figures and narrate through what multi-head attention is and provide you short information about that. But of course, I always have more details, so everything is linked. In this case, I have also this coding from scratch article, and so you can basically spend maybe a whole weekend or maybe a whole week reading through all of that if you're interested. But I thought it's just nice to have it all in one place instead of having it scattered all over my blog and GitHub and so forth. So yeah, to narrate you through maybe some interesting parts in addition to just showing you how to use this tool. So here, this is GPT-2 XL with masked multi-head attention. Nothing, I guess, you don't know yet, so nothing super interesting to talk about. For Llama 3, we have as the main novelty here, group query attention. So group query attention is essentially like a way to save keys and values, to have fewer of them. So here, this is a regular MHA, and in group query attention, we are sharing values and keys for multiple queries. And what's nice about that is it essentially makes the KV cache smaller. So if we have a KV cache, maybe I don't want to go into too much of a tangent here, but if you're interested, so in a KV cache, there are things that are recomputed in each iteration when we generate one token at a time. And so these are cached, the keys and values, so we can reuse them in future steps. Because for a given text, so if we have something like, we start with time, the LLM generates the text time flies, and then the LLM generates time flies fast. Instead of computing the keys and values in each iteration for every word, there are certain words, for example, time, it occurs in each of these generation steps. We can reuse the cached KVs. So here, in the first iteration, we don't have anything cached, so there's no cache. But in the second generation, we can actually reuse this cached time token. And then here we can, so here we compute the new flies, and then here we have 2 cached tokens. So what it means is we only need to compute each key and value once, put it in the cache, and then we can retrieve it in future iterations. And the idea here is if we have even fewer values and keys that we have to cache, if we share them among multiple queries, then it's even more efficient. We save more memory. So I think I should have a chart here so you can see in terms of complexity, computational complexity, if we have a total KV cache size here in gigabytes, and this is for multi-head attention in blue for a certain context length here. So if we look at this, it grows quadratically, exponentially, basically. So it becomes more and more expensive the longer the context becomes. But then if we have group query attention, depending on how many KV groups we have. So here we have 2 KV groups, 1, 2. We can reduce the burden on the KV cache. We can reduce the KV cache size. So here it's in terms of compression. The more groups we have, the more is shared. So the more queries use the same keys and values, the more we can compress in that sense, the KV cache. And so that's like one of the motivations behind using grouped query attention. So that was something added to Llama. Actually, it's an older concept. I think it was even already in Llama 2. So in the bigger Llama 2 models in 2023. I don't have Llama 2 here because I didn't want to go too much back in history. So here I have just GPT-2 XL as a reference point. And then here, so maybe just expand it. And here I start off with Llama 3 because I had to start somewhere. I didn't want to have like 200 architectures. So this is like, I would say, the oldest architecture here next to GPT. And then I'm planning to add all the new architectures, the main ones at least, once they come out. So to have like a starting point here. Looking further down, there are more architectures using group query attention. Some of them, like Olmo, they came a bit later, but they still use multi-head, regular multi-head attention. There's also a concept called QK norm, which is a normalization. For many of these, I have explainers. It's a bit slow right now. Here. So I have explainers short, if I have it, short from scratch code, if you want to learn more. But yeah, I don't want to go through each concept because that would be a textbook or a whole week lecture. But yeah, just maybe to continue talking about some of the attention variants. There is sliding window attention, for example. So sliding window attention is a mechanism where we restrict the width of what attention can see. So for example, here, regular attention for each token, if we have an input text, the model attends to past tokens. For each tokens, it can see the current token, so that's the diagonal, and everything that comes before it. So that's just like the regular causal self-attention mask. This can be very expensive if you have, long context looking at all the other tokens. So to make it computationally cheaper, there's a concept called sliding window attention, where it restricts in terms of how many tokens you can view. And so there are a whole bunch of models like Gemma, I would say, is one of the newest ones that is still using it. Not the only one, but I like that a lot because they have also some ablation studies. I think I have it right here, where they said basically that there is no big trade-off in terms of model performance if someone uses sliding window attention. And they also did some studies in terms of the size and everything. Now, I should say they don't only use sliding window attention. So they have like, it should say somewhere here, they should have a ratio. So for example, here, it's a 5:1 ratio. So they have 5 sliding window blocks, and then they have a regular attention block. So they call it a sliding window. They call it local because it can only see the local window, and regular attention here is the global one. And so for the global one, that is still the grouped query attention that we talked about, for example. So yeah, you can see also the layer mix. And again, the idea here is to make it computationally cheaper. And so here I have also some benchmarks, also in terms of KV cache size. So I can't enlarge this, unfortunately, but so can maybe add the plus button. So here again is multi-head attention, and then in orange is group query attention with 4 KV groups here, and lower is better. So the lower, the smaller the KV cache size. And if we compare, if we add sliding window attention to it, so you have regular multi-head attention, and then in dotted here, the dotted line, the dotted blue line is the sliding window attention. So we can see we reduce the KV cache size by a lot. And if we add sliding window attention to group query attention here, so orange solid is group query attention without, and now in dotted with sliding window attention, so you can see even stronger reductions. So yeah, so in here is the same, showing you sliding window attention with different ratios. So yeah, the more so in green should be a 5:1 ratio. The higher we set the ratio, the smaller the KV cache size, because the fewer layers have sliding window attention, basically. Yeah, so that is sliding window attention. Going back to the gallery here, where were we? We were talking about sliding window attention. Group query attention. Yeah, and mainly you find that there are some other concepts. Mainly the ones I focused on explaining are the attention ones, but I will probably add more over time. It's just, I can only do so much in a given amount of time. There's, for example, MLA, multi-head latent attention. So that was originally introduced by DeepSeek version 3. And then later, so DeepSeek version 3 came out December 24. And later architectures adopted it. For example, here is Kimi, one of the biggest architectures in terms of size, with 1 trillion tokens. And they also adopted multi-head latent attention. So that is yet another concept to reduce the KV cache size. So it's kind of like similar, or not similar, but you can think of it as, like low rank adaptation, LoRa, where you have a compressed representation, or you down project something and then you up project it. And here it's like a similar idea, but in a different context. So here what we do is we have, so let's maybe start or go back to regular multi-head attention first. So we have the input, and for each input in regular attention, multi-head attention, we have a query, a key, and a value matrix. Let's make that maybe a bit bigger. And the matrix, so the input times the matrix, it's a matrix multiplication that gives you the transformed query, key, and value matrices, and or vectors if you look at a single token. And we usually store, like we discussed before, the key and the values in the KV cache. Now, to make the KV cache smaller, to compress it, what we could do is, instead of storing the full key and value here, we could store a compressed representation of that, a compressed shared representation. And that is essentially what multi-head latent attention is. So at each step, instead of transforming it to query, key, and value directly, what we do is we have a transformation here that produces this compressed latent representation of keys and values, and that gets put into the KV cache. And optionally, you can also do that for the query. So optionally, the query is also compressed. I'm not showing it here for simplicity. And also the query is not going into the KV cache, but you can also apply the same concepts to the query. But let's maybe ignore the query for now to not overcomplicate things. So if we have the input, and then we compress it and put it into the keys and values, also not the input, but the transformed input, then later when we want to retrieve items from the KV cache again, for the next generation step, or even the current one, what we do is we up project it again. So we have another transformation here that takes this shared value and transforms it back into keys and values. Now, this whole thing is not equivalent to the one-step procedure. It's kind of like a bit of a lossy, let's say, reconstruction. It's like almost like an autoencoder, like the bottleneck in the middle. So you're not fully, let's say, reconstructing the input here that you would get when you would only do one weight transformation. So it's not like the mathematical exact equivalent, but it doesn't matter because they are trainable matrices anyways, and they would train differently. And the idea is that using two smaller matrices, we can actually get out a compressed state that we can store in KV cache more efficiently. And according to ablation studies, this works actually really well. So this whole thing, modeling performance-wise, is basically as good as multi-head attention. The downside is, of course, it's more complicated to implement in code, but and you have an additional step to project it again up. And so you can think of it almost as trading off a little bit of compute, like compute in terms of the transformation, with having some smaller KV cache memory advantage. So it's like a little bit of a trade-off, but it is usually worthwhile. So DeepSeek uses it. We saw Kimi is using it, and later architectures are also using it. So I do have also a comparison here again. So if we look at KV cache sizes, if we look at the blue one here, that's the regular multi-head attention, and then here are the different compressed states. So we can see with that we can achieve compression that is pretty significant. And here this is shown for different sizes. So we have different latent dimensions here. So depending on how big we make this compressed state, there is also a trade-off in terms of modeling performance. So it's a hyperparameter that we have to tune. The bigger the latent dimension, usually the better the modeling performance, but it's also then, of course, bigger and more expensive. And then we can go down to a very small representation. And it's essentially like something we would have to find out during hyperparameter tuning and seeing how the loss responds and how big we should set it. But yeah, I mentioned ablation studies. So this is from I should maybe add a link from the DeepSeek version 2 paper. Here I have a link. So they were showing that with multi-head latent attention, you get the smaller KV cache size, but you almost don't have any performance impact. So if you compare those two numbers here in column 1 and column 2, they're very similar. And in some cases, MLA is even better, maybe by like 1 or 2 percentage points due to maybe reduced overfitting. I don't know why exactly it should be better, but I mean, you have now two matrices, so there's also more combinatorically more you can learn if you think of it of combinatorics. So it's almost like as having more layers in a network. Maybe that helps, but maybe it's also reducing overfitting because now you have in total maybe smaller latent dimensions, fewer parameters and so forth. Hard to say. But yeah, what we can see is it's better or very similar, at least, to regular multi-head attention, whereas with group query attention here versus multi-head attention, we see that group query attention is almost always worse. It is always worse. You can see by sometimes quite a lot here, 5% points. So it is kind of worth doing MLA instead of GQA if you want to implement MLA, because it is computationally a bit more difficult, or it's another thing you have to implement. So so more ablation studies, but or not ablation, but performance studies. But so that's the idea behind multi-head latent attention. So going down, I wanted to maybe show you one more architecture because it came out recently related to that. So there was like a Sarvam 30 billion and 105 billion. So these are two models that were quite popular because they, I think, are the first really large, capable large language models from India. And what I found interesting here is that the small one, 30B, used GQA, whereas the bigger one, 105B, they used multi-head latent attention. So it's quite interesting to see that a team that has obviously implemented both, because they have architectures with both mechanisms. So it's not like, oh, this was too complicated, that's why we use GQA also for the bigger one, or for the smaller one. So they do have the implementation for MLA, but they still deliberately decided to use GQA in the smaller one. And that comes back to a point, why would they do that? And so based on what I know and talking to colleagues, it is actually when you are training GQA versus MLA, MLA is a bit harder to train. So you do need more hyperparameter tuning. And it always, I mean, I would say, or based on talking to teams working with it, when you're training it at a large scale, you only kind of see the benefits when you go up to a certain size. So in this case, I haven't talked to the Sarvam team specifically, but in this case, it looks like maybe 100 billion was a size where MLA started to perform significantly better than GQA. So I think that's maybe why the choice was made, because for the small one, MLA was maybe too tricky to tune, or was more effort, and maybe didn't give that much, let's say, advantage, or maybe it was even worse than GQA. So it's also a hyperparameter that needs to be like chosen based on other things like the model size and other aspects. Anyways, so so I think these were like the most interesting developments recently. There are, of course, a million things that happened also in the last few months. One, in addition to the attention mechanism, maybe one I haven't mentioned before, is the DeepSeek Sparse attention. That's also an interesting one, because we talked about sliding window attention. One more thing related to that is sparse attention. So sparse attention is not new. They're like, I don't know, maybe hundreds of papers talking about different types of sparse attention mechanisms. If you go back even to 2020, it's like a lot of papers out there. But most of those attention mechanisms have not been used in, let's say, state-of-the-art architectures. And DeepSeek Sparse attention, because DeepSeek is quite the big model. It's one of the most popular models out there. DeepSeek Sparse attention is actually worthwhile introducing and talking about. Here I'm actually showing GLM5, which is also using it. So it's not just a DeepSeek version 3.2 that introduced it. But the idea is similar to sliding window attention. So instead of accessing all the past tokens, so in sliding window attention, we said that we only look back to a certain number of tokens. So here I'm showing 3, which is very small. Usually it's like 512,024 or something like that, but otherwise it wouldn't fit into this figure. And DeepSeek Sparse attention is, I would say, a flavor of that, of sliding window attention, but a bit more clever. So here, instead of just saying, okay, look at the past, let's say here, 3 tokens, we can say, look at the past 3 tokens, but learn which ones. Like during optimization, like have a way to select them more optimally. Instead of just choosing 3 ones, maybe I want the first one too here. Maybe the first one is useful because it contains useful instructions. I mean, here it's literally only 1 token, but in reality you can think maybe of the first 10 tokens or something like that, because it has some instructions. So maybe it is useful to always refer to them too, and that can be learned during the optimization. So there is, if I scroll down, there is a procedure where there is like a selector and a lightning indexer that kind of smartly selects those instead of just saying, okay, we always use the last so and so many. So yeah, that's just like, I would say, an extension, almost a clever extension of sliding window attention. Going back to the gallery, maybe I said already one more thing, but there's really one more thing that I wanted to talk about, and namely that there has been like a shift towards hybrid architecture. So it started approximately with Qwen 3 Next. So what they did is they introduced a hybrid attention mechanism. So they had, instead of just using a normal group query, sliding attention, multi-latent attention module here, they now have a hybrid where they have two types of attention that they alternate. So they have gated attention, which is very similar to regular attention, except that they add a forget gate so that you can a bit more regulate what information goes through and which one doesn't go through. And they have something called a gated delta net, which is a linear attention module that is more efficient, that doesn't have the quadratic cost during inference or also during training, the quadratic cost of the attention mechanism, looking back at all the tokens. And how they use it is they have it in a 3-to-1 ratio. So layer 1 has linear attention, layer 2 has linear attention, layer 3 has linear attention. Then they have full attention. And then they have, again, 3 linear attention, 1 full attention, and so forth. And so with layer, I mean this whole box here in the center. So this is the transformer block. It includes MOE. So you can see linear attention plus MOE. So that's the whole block here. That's considered a layer. But yeah, if you look in, the reason I call it layer, or everyone calls it layer, is if you look at, for example, the config here, they use the term num hidden layers. So, they use the term num hidden layers, but hidden layers here really just refers to the whole block. And so Qwen 3 Next was an interesting architecture that kind of like introduced this concept. I mean, this concept is not brand new. There were hybrid architectures like Samba, Jamba a few years ago that did that, but it's maybe, I would say, the most, based on my knowledge, the most recent example of a state-of-the-art architecture, like a flagship, big architecture, high performance, popular architecture that adopted this. And let me go back to the overview here. And so Qwen 3 did that. And then recently, a few others did that too. So for example, Qwen 3.5 is the main flagship that also has it now. But even like Nemotron from NVIDIA, they have a hybrid now. Which else? I think, let me see, Kimi Linear should have one. I think I do have a better way to tell which ones. So if I go here and then I go to hybrid attention, I should have listed them, most of them at least. So my internet is a bit slow. There we go. So yeah, Kimi Linear is one. Ling 2.5, Nemotron. So there are multiple architectures now that have such a hybrid approach. So they do it a bit different. So here, instead of gated delta net, they have Kimi delta attention, which is, if you look at this, it's very similar. They have additional gates here, but it's not too different. It's kind of like the same idea. Some performance overviews. So here, Qwen 3.5 adopted this into the main line. Now we have a 397 billion model that does it. Lightning attention is also like a similar idea. So my internet, for some reason, loads these images very slowly today. There we go. And so they have even like a stronger 7-to-1 ratio and ablation study. And then there's Nemotron Nano. They go even further. I think they have a lot of these Mamba layers. So Mamba is a state space modeling layer. The gated delta net has been inspired by Mamba, but it's essentially like a Mamba layer with a weighted, delta weight update. But they're all like related families. They're all like, the idea is to have like a linear mechanism that does not depend on, so it doesn't have like the quadratic lookup, and also you can't, or you don't have keys and values that you store in the KV cache, so the KV cache also becomes smaller. So you have this state space model update instead. So I said the KV cache becomes smaller. There is no KV cache for Mamba layers, but you still have some group query attention here. And so you have like more like a state that you keep updating. It's kind of like, if you remember back in the day, RNNs, LSDM, so it's kind of more like that, where you have a single state where you put all the information. It is more restricted in terms of what information it has, which is why they still mix regular attention, here group query attention, and these types of Mamba layers. But the idea is that you don't have to brute force have attention layers everywhere. That would be very expensive. The idea is, how can we make it cheaper? Namely by replacing a bunch of these attention layers with these linear attention or linear layers like Mamba 2. Yeah, and I think that's like an interesting development. The motivation behind that is also, of course, that especially with agent applications like OpenClaw and so forth, we have demands for longer and longer contexts. So how can we keep the model cheap if the context becomes longer and longer? And so with Nemotron Nano, oh, I see, it should be, there's a missing N, I should fix that. Nemotron Nano. So here it's correct. With Nemotron Nano, we do have up to 1 million context support now, which is actually great, and 1 million context at a reasonable computational expense. So yeah, so that's the motivation behind it. And yeah, overall, I hope you like this. I mean, it's just a free tool, right? It's like something where you can find information, browse information. Some people like this overview figure, which I just created by putting together all the LLMs that I showed you, and asked if there is a poster. So I also made available a poster. I ordered one myself. So it is actually, my internet again is a bit slow. It is actually quite readable at this size, the medium size. So, well, it's not loading quite right now. Let me see. I don't know why my internet is so slow here. Anyway, so this is how it looks like. Maybe I will load it in a different tab. Ah, here we go. And so here, it's just, yeah, it's just barely readable in the medium size. So if you're interested in that, I would get at least medium or large on this website where I just put it up for print on demand. So if you want a nice poster, you can get one. And so I plan to update this maybe once a year with new, or remove old architectures and update it with new ones. So this is the 2025 version. I might make the 2026 version. I might make a 2027 version, update this one day. But what you have included is basically all that's shown here. But yeah, I will also more regularly update this, where I will add new architectures. For example, I'm desperately waiting right now for DeepSeek version 4. I think the rumor said it was supposed to come out in February. Right now it's almost April. I'm waiting for it, maybe for my birthday in April. That would be nice. So I will add this. And yeah, so I hope you like this. I mean, it's just like a website where you can browse things, but lots of useful information. I think there's almost too much information if you go to the detailed view. So you have a lot of information. And yeah, with that, I hope you have a good weekend, and yeah, happy coding, happy learning. I hope this is useful, and yeah, and enjoy the weekend.